Okay, going to finish up a little bit with some Chapter 15 information. Need to talk about something called conditional probability. So here is an example, a rather contrived example. You'll notice they're nice numbers. Suppose there are 500 students in your graduating class, so obviously a much larger school than Delphus Jefferson. Some students go on to pursue a college degree while others do not. The distribution is displayed in the two-way table below. So let's just make some sense out of this. By the way, we've seen tables like this in Chapter 3. So this is saying that out of the 500 graduates, 175 are going to go on to earn their college degree or to go on to pursue a college degree, while 325 do not go on. This is also saying that there were exactly 250 males in the graduating class and 250 females. So these are our marginal distributions. Recall that from Chapter 3 because they are in the margins. Then for the 75 would represent the males who are going on to pursue a college degree. And the 175 represents males who are not going on to pursue a college degree. 100 females who are going on, and 150 who are not. So that kind of gives you an idea of what those numbers represent. So let's suppose that I'm going to define event A, that it's an event that a randomly selected individual from your high school earned a college degree. So that's saying if we were to randomly select someone from the high school, so from here, what's the probability that they earned a college degree? So we're looking at, we have 175 students going on to earn a college degree out of 500. So we would take 175, that's not a decimal point or anything, out of 500, and we could reduce it or usually, get a decimal value, and this works out to 0.35. So 0.35 would be the probability that if you selected someone at random out of the 500, that that person would be going on to earn a college degree. Okay, now suppose you learned that the selected individual was a female. So I'm going to let B denote the event that a female was selected. So let's first talk about what's the probability that a female was selected. Well, the probability of that would be, we have 250 females out of 500. So that probability would be a half or 0.5. All right, so now I'm saying that we know that it's a female. Okay, that changes, that's going to change my sample space because now I'm not talking about out of all the 500 students. Now I'm just narrowing it down. I know that that person chosen was a female. So this is dealing with something called conditional probability. And what that means is given that the condition that we chose a female. So when you are doing conditional probability, you are given some condition that's being satisfied. So given that our notation we're going to use looks something like this, the probability that event A occurs given that event B occurred. So this is a notation that we're going to use. This is the part that's given. Okay, so in our example here, we're saying, given that it was a female, so this becomes my sample space, then what's the probability that they would be pursuing or receiving a college degree? So now we have 100 out of 250, which reduces to 2/5, which would be 0.4. This is called a conditional probability. So we've narrowed it down. It no longer was the entire sample space. Now it was just the females. There were 100 out of 250. So we were given the condition that it had to be a female. What's the probability that they earned a college degree? And I'm going to show you how we can develop a formula using a Venn diagram. All right, so for my example, we had A was representing the college degree. Okay, so that's this circle. And event B was the female, so that's this circle. So originally, the probability of A would be is the area of that entire circle. So the probability that they have a college degree would be the whole circle. Okay, so it'd be this entire thing. But now we're told that B has occurred. We're told we picked a female. So given that B has occurred, so let's see if I show this. Given that B has occurred, so this becomes my sample space. Given that B has occurred, I need to know the portion that has a college degree. So that only portion could be this in here. I'm given that B has occurred. I'm given that it was a female, and I want to know the probability they have a college degree. Well, it would have to be that overlapping part, which we have a name for. We call that A intersect B. So that lends us to a new formula that looks like this for conditional probability. The probability of A given B equals the probability of A intersect B, which is the part where they overlap, divided by our new sample space, which would be, because we know B occurred, so it would be the probability of B. And this is a formula for conditional probability. Now, notice that it doesn't matter what I call A and B. Say, because these are variables. So say I wanted to know the probability of B given A. Okay? The given part always has to go in the bottom because that is the new sample space. So it would be the probability of B intersect A, which, by the way, would be the same as A intersect B. But the bottom number, the denominator, is going to change because it's the given part is always in the denominator because that had become my new sample space. So that's the part that has to go in the denominator. So keep in mind when you use a formula, these are just variables. So from problem to problem, that's going to change. So let me use this definition for our problem. Remember that A represented that the person chosen was going to pursue a college degree. And event B represented that the person chosen was a female. And we wanted to find the probability that given they were a female, what's the probability that they go on and receive a degree? So our formula says that's A intersect B over the probability of B. So the probability of A intersect B would be the probability that they're earning a college degree and they're female. So we had 100 out of 500 that were a college degree female out of the total. So 100 over 500. The probability of B would be the probability that they're female was 250 out of 500. And of course, you all know that when you divide by a fraction, it's the same thing as multiplying by the reciprocal. Those cancel. We get 10 over 25, which reduces to 2/5, which is 0.4. Looking back and comparing that to what we said up here, we came up with 0.4 when we just used the table. So if you have a table, you can use the table to calculate conditional probabilities. When you don't, or sometimes you're missing pieces, and so you can use the formula. But you do need to be familiar with this formula. I need to still give you the formula sheet that you're able to use on the AP Stats exam. I haven't given it to you yet. This is one of the formulas that is on there. So, in case you forget, it's there to kind of jog your memory. Okay, moving along here. Remember, for independent events, that the probability of A intersect B equals the probability of A times the probability of B. And we use this a lot when we talked about rolling dice. The probability of getting 3 6s and we said they were independent events, so we were able to do 1/6 times 1/6 times 1/6. So if the events are independent, you can, and you want to know the and, probability of A and B, then you can multiply those together. Also, keep in mind what we just talked about. The conditional probability was the probability of A intersect B over the probability of B, which is the formula we just developed. So I can rearrange this. If I were to multiply both sides by the probability of B, okay, then that leads me to be able to say that the probability of A given B times the probability of B equals the probability of A intersect B. Okay, so I'm just multiplying by the probability of B on both sides. So I get this statement equals this. So that should not be any big deal for you, just some simple algebra. Now I'm going to use substitution. And I'm going to say this. The left side here, the probability of A given B times the probability of B equals this, but keep in mind that this right here is the same as this if they're independent events. So I can replace the probability of A intersect B with this statement here. But notice if I divide both sides by the probability of B, again, some simple algebra, I get the probability of A given B equals the probability of A. And this is true for independent events. So kind of important, so I'm going to put a box around that. All right, and I want you to think about what that means. What this is saying is, given that event B has occurred, the probability of A doesn't change. And that should make sense. We're saying they're independent. So knowing that event B has occurred does not have any bearing on what the probability of event A, it's not going to change. So this is true for independent events, and that is also a formula that you might find helpful. All right, and here's where we would find that helpful. From our example, is earning a college degree independent of gender. Now, we saw this once before in Chapter 3. We looked at segmented bar charts. We did some different things like that. And I told you at the time that we would have another way that we can kind of check it a little more mathematically, and now is that time. So if they're independent, we can check this. Is this true? The probability of A given B, does it equal the probability of A? If that's true, then we know that those two events are independent. Now, we just calculated the probability of A given B, the probability of earning a college degree, given that it was the person chosen was a female. You can look back and see we had 2/5, which is 0.4. And the probability that they earned a college degree, if you look back at our notes, what we talked about before, you'd see that that was 0.35. So since these do not equal, then my answer is they are not independent. So now we have a mathematical way using conditional probabilities that we can check to see if two events are independent.